Hello and welcome to our webinar on using the Dicom bundle to monitor Dicom performance. My name is Shama Detar and I'm a technical marketing engineer. This webinar has been previously recorded to be shared globally in multiple local time zones. Feel free to submit your questions at any time in the question and answer section. Your local ExtraHop team is available to answer your questions. We'll address as many questions as possible once we finish this presentation. So without further ado, let's get into today's topic. Dicom messages and data shown on all dashboards is created in our lab test system using a Dicom server and a Dicom client. Dicom is the fastest growing and the most profitable segment of healthcare, and ExtraHop can help. Dicom is a binary upper level protocol over TCP and uses standard ports like 104. Dicom has metadata containing the patient and provider information and the image data. The setup for Dicom can be on-site in hospitals or off-site as a radiological service. Dicom environment has a radiology information system called RIS or a hospital information system called HIS, modality worklist server, a picture archiving and communication systems called PACS server, and client workstations. Dicom modalities are the different types of images like X-rays, CT scans, MRIs, etc. that can be stored with commands like cstore on the PACS server. The radiologist can get the images onto their workstation using commands like cfind, cmove. This Dicom bundle contains two triggers that create three different dashboards and can create EXA records for all Dicom request and response transactions. Dicom widgets in the dashboards are arranged such that the left widget will show counts, the center widget will show counts over time, and the widget on the right, which is the text widget, has an explanation of what we see in the left and the center widget. Let's start with the Dicom overview dashboard. We're going to look at the top two rows that show the Dicom request, responses, and aborts over time as counts and over time. This gives a good idea as to what is happening in the Dicom environment. How many responses, how many requests, how many responses, and how many aborts, if any, were seen. Aborts can be caused by generic networking issues like wrong IP address, wrong port number, firewall blocking, or slow network link. Aborts can also be caused by Dicom-specific issues like conformance statement mismatch, unknown device names, duplicate application entity titles, permissions not given to store or query, or bad message syntax. So that's what we saw in the first top two rows. Now let's look at the request and response message formats as count and over time. Protocol data units or PDUs are the message formats exchanged between the peer entities within a layer. PDU is an application level packet that says how big the received buffer is. Association is a Dicom handshake between the two application entities, which starts the network communication channel between them. Dicom association rules are built on top of TCP/IP to make decisions about the message formats. There are 7 different PDUs in the Dicom upper layer protocol. These PDUs are associate request, associate response accept, associate response reject, request and response data transfer that contains the data, and release request, release response, or response abort. So that's what we are seeing in this row here. The next two rows will show request counts by called and calling IP addresses, and the response counts by the called and calling IP addresses. In a live production environment, you will see multiple IP addresses. Since this is test data, we are seeing only one. Dicom network has two communicating nodes called the application titles or application entities that have application titles. These application titles must be unique, they're case sensitive, and they can be maximum 16 bytes. The application entities have a IP address and a port assigned. The called application entity is like a server, and the calling is like a client. Request and this is what we see in these two rows. So we can see a breakdown of the calling IP and called IP, and we can see how many requests and how many responses. The last row on this dashboard shows the request status. The request status, the different counts that we see here and the information that we have here helps in troubleshooting, especially when upgrades or new installs happen on a system and then what used to work before just stops working. So this can give us a good idea as to what could be causing problems. Aborts can happen, like I mentioned before, because of generic networking issues or Dicom specific issues, or the connection is closed before the request or response is complete. Errors, if present, these are the detailed error messages recorded by the ExtraHop system. Dicom versions, the current version is 3, but many of the systems still use 0 and 1 as their versions. If there is any mismatch in this version between the two communicating application entities, then communication cannot happen. So this information will help troubleshoot in that if we see such problems. What I'm going to show you now is if there is an EXA and if you wanted to create EXA records for each request and response, then you can. Here is an example showing a Dicom request, and these are the different fields that can be stored from that particular request. Similarly, for Dicom responses, we can create EXA records. Now let's move on to the next dashboard. Here we are looking at the different Dicom messages. Request and response is split in each row that you see here. Request by calling AE title and by called AE title. And the same, so request by calling AE title over time. As I mentioned earlier, there are 7 different PDUs, and this dashboard shows the Dicom messages broken down by the 7 different PDUs. Dicom messages have command set followed by conditional data set. The connection of a Dicom client to a Dicom server is called an association. And it's a handshake when the client and the server agree on the type of commands transfer syntax, services that can be exchanged between the two. That actually starts the communication. So the communication starts with association request. An AE title is used by an application entity to identify itself. AE titles must be locally unique, can be maximum 16 bytes, and are typically managed by the system administrator. AE titles of the application client should be made known to the server it wants to connect to. And the server should have, or the client should have, the proper permissions given so that it can communicate with the server. So this is the breakdown that we see. Also, application entity is a service class user, which is the calling or the client AE title, and the service class provider, which is the called or the server AE title. So what we are looking at here, associate request by calling AE title. So this is like a client, and called is like a server. So this shows counts and then the distribution over time. So first two rows are for associate request by calling and called AE titles. Then is the associate accept responses by calling and called AE titles. If for some reason the association cannot happen, then you would see rejects, which we don't see here, and if everything is working, we should not see the rejects. Then the actual data transfer happens between the calling and the called AE titles. So these are the request and responses for the data transfer. And once the data transfer is complete, the release request is sent by the calling title, and the release response happens after the release request is sent. If everything is working, we should not see any abort responses, and that tells us that the communication happened, the data transfer happened, and everything is running smoothly. So this is what is shown on the Dicom messages dashboard. Now we'll move on to the last dashboard, which is the Dicom network dashboard. The metrics that we see here will help us in troubleshooting if there are any problems. Where are the problems? Is it on the network, or is it on the Dicom server or the application? The first row shows the request and response counts and request and response counts over time. This again gives us a general idea as to what is happening in the Dicom environment. The second row shows the network throughput counts and the network size packets and size packets over time. Network throughput and packet charts will generally display similar patterns in a line chart. If the line patterns are dramatically different, it generally indicates that small size packets are being sent. In the next row, we show the 95th percentile Dicom processing time and the network time. We also show the application entities with the slowest processing time. This chart displays the performance of the slowest 5% of the transactions. Each application entity has a unique IP address assigned to it. If the processing time is high, then the receiving system might be under-provisioned. The next row shows Dicom response processing time, network time, and errors over time. In this case, we don't see any errors, which is a good sign. The network time is measured in round-trip time metrics, and it calculates the total amount of time the message spent traveling between the sending and receiving systems. The processing time is the total amount of time taken by the receiving system to receive, process, and return an acknowledgement for the message. The next row, in addition, the charts also display the failed messages if they occurred. This might reveal if the errors on the systems are correlated to the timing of these metrics. Since we don't see any errors, that's a good thing. The next row shows request and response transmission timeouts, or RTOs. RTOs can occur when the sender is missing too many acknowledgements and decides to take timeout and stop sending for some time. As a result, RTOs can cause delay on the network and affect the application performance. The next row, request and response transfer time. If the request or response is contained in a single packet, the transfer time is 0. A high value might indicate a large request or response or a network delay. The last row shows Dicom network request zero windows. No zero windows seen is a good sign. A turn represents one full cycle of client transferring request data, followed by the server transferring a response on every TCP or UDP turn. These are the numbers of zero window advertisements sent by the client. A device advertises the zero window when it cannot process incoming data as quickly as it is arriving. At its extreme, a zero window occurs, indicating a stall of the application and its inability to accept any more data. So that finishes up this webinar. Thank you for joining us today. And now we will change to the question and answers portions of this webinar.